Hello everyone, it's my honor to present our paper PVT-SSD, Single-Stage 3D Object Detector with Point-Voxel Transformer. This work focuses on 3D object detection on litter point cloud, which aims to localize objects and identify categories. To process unordered point clouds, Transformer has recently attracted great interest. To reduce the computation complexity, some point-based methods perform attention on downsampled point sets, while some voxel-based methods employ attention on local voxels. However, downsampling requires time-consuming farthest point sampling, while voxelization loses accurate position information. Instead of sampling points directly, we convert points to a small number of voxels and sample non-empty voxels to reduce the sampling time. Then, voxel features are adaptively fused with point features to make up for the quantization error. Finally, we design virtual range image to enable quick neighbor search. Unlike previous transformer-based indoor 3D detectors, our target application is for outdoor scenes where point clouds are sparse and large-scale. Thus, we use sparse convolutions as the backbone for efficient feature encoding. Then, we propose query initialization that samples voxels instead of points to reduce the sampling time. Meanwhile, we make the voxels near objects more likely to be sampled, which can further boost the detection performance. Specifically, the module has two branches. Branch 1 samples 2D non-empty voxels and lifts the 2D voxels to generate 3D reference points. Branch 2 first constructs the dense feature map through several convolutional layers and then indexes features in terms of branch 1's coordinates as content queries. The Point-Voxel transformer takes four inputs: reference points, content queries, raw points, and voxels from the 3D backbone. The voxel tokens and point tokens are generated, which are then fed into several transformer blocks to adaptively captures long-range contextual features and fine-grained geometric features. For voxel tokens, we randomly sample L voxels from the middle layer of the 3D backbone within a large radius of reference points. For point tokens, we apply the ball query to sample L points within a small radius of reference points. However, the sampled points only contain XYZ position information, lacking local geometric and contextual information. Thus, we interpolate the features of 3D voxels near the points to obtain point features. For point token generation, we introduce a novel ball query to quickly find neighbors of reference points. For each reference point, it is first uniquely transformed to the litter spherical coordinate system. Then it can easily find their neighbors based on range image coordinates. As the point clouds are from multiple frames as well as multiple litter sensors, various points may overlap on the same pixel. To overcome this issue, each pixel of our constructed virtual range image is an array of indices pointing to overlapped 3D points. For convenience, we organize overlapped points adjacently and record their start and end position indices. With the constructed image, each reference point can find neighbors according to pixel positions. To prevent the distance between adjacent pixels from being large in 3D space, we will check whether the neighbors are within the radius of the reference point. During the process, we will apply a random selection algorithm to retain at most k neighbors. We compare PVT-SSD on the Waymo dataset with previous methods. We divide current methods into the branches of one-stage and two-stage detectors for comparisons. Table shows that PVT-SSD surpasses previous one-stage methods with a single-frame litter input. The performance is also comparable with state-of-the-art two-stage methods. Table illustrates the performance comparisons on the official Kitty test server. It shows that PVT-SSD has the best car detection performance among all single-stage detectors at both easy and moderate levels. Compared with previous transformer-based detectors, PVT-SSD is 1.4 times and 4.4 times faster in inference speed than CT3D and VOTR-TSD, respectively, and achieves better moderate AP. It also requires less number of parameters. We conduct a series of ablation experiments to comprehend the roles of different components. Table 1 shows that lifting plays an essential role in query initialization. It can not only make 2D voxels into 3D points, but also can bring reference points closer to the center of the object, which can make it easier for subsequent regressions to recall their corresponding 3D boxes. We can find that the voxel tokens and the point tokens provide improvements of 0.45 and 1.58 APH, respectively. And the improvement brought by the point tokens is larger than that of the voxel tokens, which is intuitive since fine-grained point features are essential for accurate box regression. Table 2 ablates the influence of radii, which will affect the receptive field. We observe that large receptive fields improve detection performance, but it is not further improved when continuing to increase the receptive field. It may be due to the fact that more irrelevant noise points are sampled while relevant points benefiting detection are randomly discarded. We compare the latency of our range view-based ball query with that of the original ball query, where the kernel size is set to 16 to find 32 neighbors within a radius of 0.8. It shows that the range view-based ball query performs well as the point cloud increases and achieves a speedup of 29.7 times over the original ball query when it is applied on 200K point clouds. We also show the attention weights of the sampled tokens for each reference point. The model can capture object-centric features and long-range features. We find some failure cases of our method. For example, small objects, such as pedestrians, are sometimes not detected. These objects usually occupy fewer voxels than other objects, causing them to be less likely to be sampled. In the future, a better query initialization module could be designed to improve the quality of the reference points to recall the corresponding objects. This is the end of our presentation. Thanks for your watching.